Much falls into place by considering 17th century physics as mechanistic in the sense of a mathematization of physical magnitudes after the model of rational mechanics. That is, as opposed to the view that exaggerates the value of experimentation in early science. The rational mechanics of Archimedes that adapts the deductive proofs and diagrams of Euclidean geometry to include the qualities of weight and the balance of physical magnitudes. When used as a standard for an exact treatment of mathematical physics, aligns with an epistemology very different from the inductive epistemological paradigm of experimental physics. We find that the kind of physics which would have been called a mixed mathematical science, as also were optics and mechanics, contextualizes and fits rather well with the epistemological speculations of the early modern philosophers. Otherwise, the epistemological projects of discovering a method, which so much occupied the minds of 17th century philosophers, seem to be looking in an altogether different direction than the physics of the new science. The musings of Descartes, Hobbes, Leibniz, Locke, and other early modern philosophers are wrongly seen as isolated chance speculations, or at best are seen as a sort of correspondence amongst philosophers disattached from the scientific revolution. But that is because there is no relation between the proclaimed scientific method of experimental physics and the epistemological project of the Cartesian method, of a mathematical physics that virtually equates algebra or mathesis universalis with physics. And there is no relation between the proclaimed scientific method and Hobbes' deductive physics styled after a demonstrative science. But here is not only what can't be explained by an experimental, empirical, scientific method, but what would have to be. That Newton presented his Principia Mathematica as the laws of nature deduced geometrically. That's the form they were thought to have had to be arranged in, not only in order to amount to an exact science, to which the experimental inductive method might well pretend, but to secure absolute certainty, or so they thought or aimed. Without inheriting that sort of epistemological rigor, modern science would not even be equipped with the concept of a fact as something indisputable. That sort of finality and certainty, accompanied by the concept of a fact, for example, bastardized though it be, is derived from the epistemological project of Descartes, among others, in their quest to determine a method which could detect and secure certain scientific knowledge. Thus, without those epistemological musings and speculations and searches for a method within early modern philosophy, there would not be the kind of certainty that has been received in scientific discourse, nor would science, and by that I restrict myself to physics, be something which is indisputable, and something which can even feign certainty. What also reveals that the idea of the scientific method as centered primarily on experiment is misconstrued is that contemporary scholars marvel at the fact that physics has obviously been mathematicized. They speak as if that process of mathematization must have occurred relatively recently, and speak of mathematical physics as a sort of chance occurrence that could have been otherwise, when in fact Newtonian mechanics, the very core of modern physics, was presented in the form of not just mathematical, but geometric deductive proofs. Contemporary scholars also are in awe about the mathematical appearance of scientific formulae in the cipher code of algebraic equations, when all along the father of modern philosophy and inventor of specious algebra set himself to the task of designing a mathesis universalis to, quote, solve all problems, and considered physics to be quite literally a branch of mathematics. Now, such a physics conceived as what were called the mixed mathematical sciences might well have used experiments here and there, as rational mechanics might resort to an actual balance at time. In the sort of way that mechanics uses diagrams to aid deductive proofs, but that would not factor into the criterion of certainty. There is a reason why each paradigm of science is defined as a new kind of mechanics. Thus, the physics of Newton was termed Newtonian mechanics. And now we have the sci-fi version, which still defines the whole paradigm of science as a mechanics, in quantum mechanics. But the significance of what mechanics was has been lost. And that resulted from work ceasing to be done in statics in favor of a focus on dynamics and kinematics, the other branches of mechanics. For only statics provides a model for adopting physical magnitudes, and especially their quality of weight, to geometric proofs, accompanied also by geometric diagrams. Kinematics and dynamics, although forming a mathematical science of nature and of motion, do not so neatly conform to geometry, nor to mathematics. The appeal that rational mechanics had on the early modern mind was the promise of an exact science, as well as the certainty that follows from deductive inference. Again, the appeal that rational mechanics had on the early modern mind was the promise of an exact science, as well as the certainty that follows from deductive inference. Aristotelian physics is not an exact science. Of course, Aristotelians allocate a place to mixed mathematical sciences. But physics functions for them dialectically. That is, disputations in language decide questions like when water becomes air, whether one substance ceases to be and another comes to be, or whether a single substance underlying both merely undergoes alteration. Aristotelian physics is then not mathematical, as disputing over the principles of nature. The minds of the 17th century were dissatisfied by endless disputations over dilemmas of scholastic physics, over problems verging on paradoxes, as whether motion is continuous or discrete. Thus, what appealed to them was the exact science of mechanics, to the problems of which there is always a direct line to finality. But optics also, being ranked along with mixed mathematics, is an exact science and treats of visual rays not insofar as they are beams of light, not even insofar as they are light, but insofar as they are lines. Thus, in optics, there was never any dilemma about whether light is composed of particles or waves. That is even laughable, if not outrageous, from the standpoint of mixed mathematics, and would compromise the certainty and rigor of that science. Optics, as an exact mathematical science, can only consider rays of light insofar as they are lines, geometric lines, without breadth, and insofar as they refract along rectilinear angles. As such, optics was found to be useful in art, as in the famous works of the Renaissance of De Perspectiva and De Pictura. Astronomy also has always been an exact mathematical science, concerned only with the motions of the luminaries insofar as they take place along curvilinear lines and have proportional orbital periods. The same goes for the study of the musical intervals, which considers nothing but the mathematical ratios of different pitches. But mechanics has also, along with that, a practical application in effecting great feats. Thus, all the mathematical sciences are exact sciences and have as their subjects physical things, but consider them only insofar as they are linear or as they have proportional ratios, that is, as they are mathematical, not insofar as they are physical, and doesn't speculate about the composition or physical concerns of any of them. And that is what appealed to the 17th century mind. A corpuscular explanation of rays of light in optics, or of waves of sound in harmonics. I mean the explanation, for example, that light is composed of atoms or particles, would result in the loss of exactitude and would cease to be a mathematics. Notice that observation and experiment play hardly any role in them, but are required to supplement the mathematics. Thus, Aristotle says that they are not altogether identical with physical problems, speaking of mechanics, nor are they entirely separate from them, but they have their share in both mathematical and physical speculations. For the method is demonstrated mathematically, even geometrically, but the practical application belongs to physics. However, not only are they exact mathematical sciences, but theorems in them are proved deductively. Hence, the claim to certainty. Thus, Archimedes supplied proofs which carry with them the certainty of deductive inferences, even when he so often uses reductio ad absurdum, rather than syllogisms in the first figure. Although Aristotelian physics is full of syllogistic deductions, each premise in Aristotelian physics being composed in language and about incredibly lofty speculations may be separately objected to in a way that leaves room for endless disputations, even as to the details of a theory that disputants agree upon, which was unsettling, to say the least, to the talented minds of the 17th century. They did not want to have anything to do with dialectic, and they wanted the exactitude of mathematical physics, or of the mixed mathematical sciences, which were already in place in the case of optics, astronomy, harmonics, and mechanics. They were styling their new science after them. The early modern philosophers, who have been presented as concerned with epistemological and metaphysical programs as isolated speculations detached from the scientific revolution, are misunderstood, because the rationalist project of a mathematical physics styled after the science of mechanics has not been recognized. Oddly enough, the philosophers are presented as accepting the challenge of formulating the new science, and yet having theories about epistemological methods of knowledge separate from that. I mean that the physics of Hobbes, Descartes, Leibniz, and the like are taught as being something uninfluential and as not a part of their philosophical work. Yet natural philosophers of physics were up to the time of Newton, either Cartesian, Leibnizian, or atomistic, following Gassendi, or perhaps Boyle. That is in the days of Wolff and Huygens. All of them thought that certainty was restricted to what could be formulated after the manner of rational mechanics and the mixed mathematical sciences. They thought physics should be restricted there too. That nothing should be admitted to physics which cannot be formulated mathematically. That was all in line with the Cartesian epistemology, whereby certainty is first restricted to mathematics, and then mathematics is extended into physics. They weren't settled by dialectical arguments in physics hinging on categorical distinctions and the definitions in terms of language. They perceived scholastic disputations as scholastics would have perceived sophistical arguments, whereas they falsely accused scholastic physics of resorting to occult powers. Their real suspicion of the physics of the schools was that the terms or the words with which syllogisms were composed might be used equivocally and have ambiguous meanings. Since that is a pitfall that leads to sophistical arguments, they suspected all arguments in language to be likewise susceptible to indeterminate definitions. And they were generally unsettled by dialectical disputation as a method of proof and disproof. The mechanistic terms, such as size, weight, speed, and all quantities, however, they supposed to have obvious and undoubtful meanings. So with mathematics as the exemplar of certain knowledge, they sought to model the new science after the mixed mathematical sciences, which were even indeed categorized by Plato as mathematical sciences in and of themselves. Secondary, however, and dependent upon geometry and arithmetic, yet had as their subjects physical things in a different sense. And those exemplars of a sort of mathematical physics which were already in place proved their theorems deductively, as well as carried an exactitude about physical things which could otherwise not be attained. They provided to thinkers like Galileo, who famously wrote most about mechanics, Hobbes, Descartes, and Huygens, among others, a clear passage from the certainty of mathematics to an exact mathematical physics, which was lacking not in certainty. Thus, a mathematical physics, or rather physics considered as a part of mathematics, attains to the epistemological certainty of the Cartesian project, which again called for a deductive mathesis universalis that identifies physics with mathematics, or a part thereof. And that was how physics was performed by Huygens, Malebranche, Wolff, and the other natural philosophers during the 17th century. That is also whence a tendency arose to restrict certainty and scientific knowledge to science. that is physics. And this is important, that is also whence the tendency arose to restrict certainty and scientific knowledge to science, that is physics, insofar as physics is mathematical and deductive. For that is the most peculiar phenomena that cannot be explained otherwise. That certainty and scientific knowledge have been restricted to science. That cannot be explained otherwise than Descartes' method of doubt, finding that mathematical knowledge alone can be certain, and that physics can be treated thus. Briefly, I should reiterate that such a certainty as Descartes planned for a mathematical physics does not allow optics to speculate as to whether light be composed of particles or waves, but optics must consider rays of light insofar as they are lines. Neither can that kind of certainty speculate about the force of gravity, but must be content to mechanistically formulate the acceleration of falling bodies as a mathematical ratio. That was not allowed even by the greatest natural philosophers of the 17th century. But we are here not attempting to show where physics has gone off the rails, but what the original project was. And that also further shows that they didn't just come out of the same dilemmas of scholastic physics on the other side than those argued for by the Peripatetics, but they meant to altogether avoid anything that could be a topic of disputation. Whence they avoided dialectic and arguments about the structure of things, lest they be mathematical and lest they be subject to the certainty of mathematics that can have a sort of finality, which argument, we wouldn't say that argument is lacking in that respect, but that mathematics has a sort of simplicity which does not hinge on the definitions of terms, or in which the definition of terms is less a matter of dispute than the definition of what substance is, or what an essential attribute is, when that factors into a disputation.